Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over an example problem where they are asking you to find the concentration of the anion of a diprotic acid. And in this case you're going to have to do your ice chart twice. So you'll have to do the ice chart once to find the concentrations of your H plus ion and the ion for the anion that's left over with the second proton. So for example, you'll have to do an ice chart for this first equation here where you lose one proton and form your hydronium ion. And then you're going to have to do a second ice chart using that information to figure out the concentrations of these two here, and this is the concentration we are looking for. So you got to do it twice. So here goes the first one. So we're going to set up our ice chart here, right? So the initial concentration is the concentration of our acid, the diprotic acid. So we have 0.100 molar. We don't need to write the molar, we'll just 100. And then our concentrations of, we're looking at this here. So that's the concentration of this, and then the concentration of this is going to be 0 to begin with. So right now we're looking at this equation here. And our concentration of H3O plus is negligible, so we're going to say 0 there. And then our change, we're going to lose some of the acid and we're going to gain some of the conjugate base plus X and some of the hydronium ion plus X. It's all a 1-to-1 ratio here, so it makes it easier. So it's negative X plus X plus X. And then we add these together to get the equilibrium concentrations in terms of X. 0.100 minus X, and then you get plus X again. And now we can set up our Ka expression. So Ka1 is equal to 8.0 times 10 to the negative 5, which is going to be equal to the concentrations of these two. So H3O plus concentration multiplied by the HC6, H6O6 minus concentration all over the concentration of this acid here. So it's going to be H2C6, H6O6. So we have X's for these two. So that means 8.0 times 10 to the negative 5. Will be equal to X squared over this value here. So that's going to be 0.100 minus X. And here we can do the X is too small approximation. It will work because our starting concentration is much different from the Ka value here. So X is too small. And then multiply 0.100 by both sides, square root both sides, and you should get X is equal to, give me a moment, X is equal to 2.8 times 10 negative 3. So 2.8 times 10 to the negative 3. If we divide this by the original concentration and multiply that by 100, we get a percentage of 2.8%. So 2.8%, that's less than 5. So the X is too small approximation is valid. Okay, so now now we have, this is the concentration of H plus or HCO plus, and it's the concentration of this leftover conjugate base. This is what we're going to use for our next ice table for the second equation. So now Now we're at the second equation. So let me put a line here. And so we're going to do another ice table. But this time we're looking here. So our starting concentration here for this is this here. So we have 2.8 times 10 to the negative 3 because that's what we ended up with here. So we have this and this. Now we got to bring that back down here. So this is our starting concentration here. And now the starting concentration of this species here is 0 because we don't have any at the beginning. And then our H3O plus concentration is X as well. So that's going to be 2.8 times 10 to the negative 3. Okay. So now we have our starting concentrations here, and now we do the change again. So again, we're going to lose an X amount here. The stoichiometry is 1 to 1 to 1. So we're going to lose X here, we're going to gain X here, and we're going to gain X here. So when we add these together to get the equilibrium expressions, we got 2.8 times 10 to the negative 3 minus X. Here we have plus X. And then here we have 2.8 times 10 to the negative 3 plus X. And so here are the equilibrium concentration expressions. And now what we need to do is use our Ka2 value to set up Ka2. So Ka2 is equal to 1.6 times 10 to the negative 12, and that's going to be equal to the concentrations of these two, H3O plus and C6H6O6 minus. So we have H3O plus concentration times the C6H6O6 minus concentration all over the concentration of this species here. So that's going to be HC6H6O6 minus concentration. And so now all we need to do is plug these expressions, these equilibrium expressions, into our Ka2 expression. And so what we have here is going to be 1.6 times 10 to the negative 12 is equal to, and these two, so it's going to be X times 2.8 times 10 to the negative 3 plus X over, and then we have this expression here, so that's going to be 2.8 times 10 to the negative 3 minus X. And then so we can do the X is too small approximation twice, here and here. So the amount you lose and the amount you gain is negligible to these. So cross that out. And then when you cross that out, these two cross out. So that crosses out, that cancels out. And so X ends up equaling 1.6 times 10 to the negative 12. And of course, if you take this, divide it by the original concentration, multiply that by 12, that's going to be much, much less than 5%. So this is valid. So X is equal to 1.6 times 10 to the negative 12. And we know that X is the concentration of our anion that we were looking for. So this is the concentration of the anion for this acid here. I hope this makes sense. I hope this was helpful. If you like the videos, if you like my videos, please like, share, subscribe, hit the notification bell, make a comment in the comment section Thanks for joining me, and I'll see you next time.